This is our second to last module where we'll be talking about the completeness theorem for first order logic. So, just a few words about the people behind the completeness theorem before we go into the details of the proof. First, the mathematician who's credited with proving the completeness theorem is Kurt Gödel, and he proved it in his PhD dissertation in 1929. He was originally an Austrian mathematician and worked in Vienna, eventually immigrating to the United States and working at the Institute for Advanced Study. Tarski was able to begin to simplify the proof of Gödel by introducing the notion of a structure, which is what we've been talking about. And he is the first to give an account of the notion of satisfaction in truth. And that's the sort of starting point that we'll have in the next few slides. Working off of Tarski, Henkin in 1939 established a new proof of the completeness theorem that uses the existence of a certain mathematical structure, which we'll call the Henkin construction. And it vastly simplified the proof, and it's the typical proof that is now used in most mathematical logic books, although there are many different versions of the proof of the completeness theorem. Kurt Gödel, 1 year after the proof of the completeness theorem, went on to prove something called the incompleteness theorem, which we'll explore a bit in our next module, our final module. And Tarski and Henkin sort of joined forces with one another and started a school at the University of California in Berkeley called the School of Logic and Methodology of Science, which produced some of the most famous logicians of the past century. So we'll follow the footsteps of Tarski and introduce the notion of truth in satisfaction for our mathematical structures or our first order structures. Recall that a first order structure, which is here denoted by this fractor M, is a function whose inputs are basically symbols from the first order language L. Now, among those symbols are the universal quantifier, the predicate symbols, the function symbols, and the constant symbols. On the other hand, the variable symbols are not included in the definition of a structure. Instead, they're intended to be quantified over when you're using a universal or an existential quantifier. Now, in order to define the notion of truth and satisfaction in a recursive manner, we need to somehow assign names or objects to our variables temporarily. And the way that we'll do that is through a variable assignment. So a variable assignment for a structure M is going to be just a function g whose domain is some subset of the variables and whose range is the domain of discourse. So basically, it takes as inputs some of the variables from our language and outputs elements of the domain. And what it does is, for a moment, it treats a variable sort of like it's a constant and that it actually names some object in the domain of discourse. Remember, the domain of discourse is the what we've been labeling here in this case D, but it's the output of this first order structure when we that function at the universal quantifier. Now, as a nice example, let's suppose we have a mathematical structure and that our domain of discourse was just a 3-element set, and in this case, a really simple one, the set consisting of the numbers 1, 2, and 3. Now, let me give you a few examples of some variable assignments so you can get a better idea of what they might look like and the fact that the domains don't always have to be the same. So the first one we'll look at is what we're denoting by G1, and it's a map that takes the variable x to the number 1, and that's it. Doesn't do anything else, doesn't map any other variables to any other places. It's just taking that single variable, that's its domain, to that element of the domain of discourse, which is 1 in this case. Now, a slightly more interesting sort of expanded variable assignment might be this one, which we're denoting by G2. And in that case, it maps the variables x, y, and z to 1, 2, and 3, respectively. So it sort of, in some sense, extends G1 so that it's now sending y and z to the elements 2 and 3. But we're free to send these elements wherever we would like. And so, for example, we could even send them to the exact same elements of the domain of discourse. So, for example, G3 here takes x, y, and z and sends them all to the same element 2. And again, remember, what we're sort of doing here with our variable assignment is temporarily thinking about the variable as sort of being like a constant and naming an actual object in the domain of discourse. In this case, we're sort of assuming x, y, and z all name that object too. And then finally, because the domain of discourse can be any subset of the variables, it could very well be that the subset is empty. And we have a special name for this particular variable assignment. We'll call it G0. And I'll always use that same notation here for the variable assignment whose domain is the empty set. In other words, it doesn't assign any values to any variables at all. In addition to the variable assignments themselves, we'd also need to be able to modify our variable assignments by changing their outputs variable by variable. And we have a bit of notation for that. So let's suppose that G is a variable assignment, X is a variable, and that A is some object in the domain of discourse. And we'll be using this notation that you're seeing here, a G and then a bracket X / A and then a close bracket. To denote the variable assignment, so it's a new variable assignment, whose domain is exactly the same as G, plus the variable X. So we're throwing X into the domain of G, and it assigns exactly the same values as G, except that the assignment now maps the variable X to this new element A inside the domain of discourse. Now, just to sort of use this notation on a couple of the variable assignments that I defined on the previous slide, if we look at, for example, G0, remember that was the variable assignment that had no variables in the domain. Well, if we adhere to its domain, the variable X, and we stipulate that it must be mapped to 1, which is what you're seeing on that sort of first line down there, well, what you get back is the variable assignment G1, the assignment that takes the variable X to the number 1. We could also then modify G1 by stipulating that we add in both Y and Z into the domain of G1, and we map Y to 2 and Z to 3. And that's what's being sort of said on that bottom line. And if you recall, G2 was exactly the assignment, the variable assignment that sent X to 1, Y to 2, and Z to 3. So here you have sort of a nice sort of calculus or algebra of these variable assignments and how to change them sort of variable by variable. And we'll need that sort of change in order to define satisfaction for the universal and the existential quantifier. So we have just 2 more pieces of notation that we need to define before we can go on to giving the sort of recursive definition of satisfaction for a general sentence in a first-order language. So here, given a well-formed formula P, we say that a variable assignment G is appropriate for P if all of the free variables of P are in the domain of G. So any of the variables in this well-formed formula that haven't been quantified over, this variable assignment will assign elements of the domain of discourse to them. So just as an example here, our assignment that we've been talking about, G1, which sends the variable X to 1, would be appropriate for any well-formed formula P, which had just a single free variable X. G2 would be appropriate for any well-formed formula P whose free variables are any subset of X, Y, and Z. And remember, G2 sends X to 1, Y to 2, and Z to 3. And notice that it's appropriate even for subsets of X, Y, Z. So you could have more variables in your domain, but the notion of appropriate just means that the free variables in P are within that domain of G. So not just that it's equal to the domain of G, but in fact are in the domain of G. And then with that said, that means that G0, the variable assignment whose domain is the empty set that doesn't assign any variables to anything, is appropriate for any sentence in our well-formed formulas. And remember, a sentence is one that doesn't have any free variables. And that's the only sort of well-formed formulas that it would be appropriate for, because if it had a free variable, then it would definitely not be within the domain of G0. The last piece of notation that we'll need is just a matter of some notational convenience. If we have some term in our first order language, which we're sort of assuming in this case, or we're sort of making this assumption that there are no function symbols. We'll come back and revisit that assumption later on, but for the moment, we'll assume that there's no function symbols. And so our terms are either just going to be our constants from the language or the various variables in the language as well. Now, the first order structure M tells us how to interpret the constant symbols, and the variable assignment G tells us how to interpret the various variables. And so we can combine the two of them together into a single sort of notation here. If you have a term T, you can put two brackets around it like we have here to denote M of T if T is a constant, and G of T if T is a variable. And that's, again, just a nice way to encompass both the sort of variables and constants all in one notation. Now, the textbook adds a superscript of an M and a subscript of a G just to emphasize the fact that this depends on M and G, but the only place that we'll see it in our slides is basically on the next slide when we're dealing with satisfaction for atomic sentences. And so really it's just sort of a bit of notational convenience here so that we don't have to write too many terms. And again, that nice curly bracket that you're seeing there is not a curly bracket for a set, but instead for a piecewise defined function. And again, here the output of this function is M of T if T is constant, and G of T if T is a variable. And again, those are the only terms that we'll be considering in this first order language, which we're implicitly assuming has no function symbols. We're now ready to look at the recursive definition of satisfaction. And by recursive, what I mean is that we'll define the notion of satisfaction first for our atomic sentences, and then we'll build up the complexity applying our truth functional connectives and our quantifier rules for building up more complicated well-formed formulas. And along the way, as we apply those various rules, building up these more complicated well-formed formulas, we'll say exactly what it means for a structure in a given appropriate assignment to satisfy that given well-formed formula. Okay, so being a bit more precise, let's let P be a well-formed formula, G be a variable assignment in a mathematical structure M, or a first-order structure here, and that this variable assignment is appropriate for P. Remember, that means that any of the free variables that are appearing in P are within the domain of G. And so they get assigned a value of the domain of discourse by that function G. On the other hand, M also assigns a element of the domain of discourse to each one of the constants within our first order language. And therefore, together they assign a element of the domain of discourse to any one of the terms, either a constant or a variable. That's that sort of notation that we looked at on our previous slide. So let's suppose we're in the atomic case, and the well-formed formula that we're looking at is just an application of a single n-ary predicate. Now, we'll say that the well-formed formula P of T1 through Tn, so this is plugging in terms T1 through Tn into our well-formed formula P, is satisfied, or G satisfies that well-formed formula in our structure M, if and only if the n tuple consisting of these values of the terms t1 through tn, either by the structure m when they're constants or by the variable assignment g when they're variables, is an element of the output of P for this given first order structure. That would be M of P. And remember, M of P is a collection of n tuples, because in this case, it's an n-ary predicate. And so basically what we're saying is that if, this collection of terms actually was inside of this output here, one of these n tuples, well, then we say that G and M satisfy that particular statement. And what we'll write is in terms of a double turnstile, like we did back in chapter 8 when we were introducing the notion of tautological consequence. Here we'll use this notion for logical consequence. But for now, when this G satisfies P and M, we'll first write the structure M, the double turnstile, the formula P with those terms T1 through Tn, and then in brackets the variable assignment G. And again, remember that pretty much whether or not that statement is true depends on M, P, G, and the terms T1 through Tn. Okay, so that's how we use the structure and that sort of definition to first build up what atomic sentences in our well-formed language are sort of on our first order language are either true or false. True meaning that they're satisfied in the structure, and false meaning that they're not satisfied in the structure. Okay, so let's now talk about each one of the truth functional connectives one by one. First off, again, we'll assume P is a well-formed formula and G is a variable assignment in our structure M, which is appropriate for P. And we'll further assume P is the negation of some well-formed formula Q. Now, because Q has one less connective, we could assume that we've already defined the notion of satisfaction for Q. And if it has no connectives at all, then it's an atomic sentence, and we defined it on the previous slide. Now, we'll say that G satisfies P and M and write it down here in terms of this double turnstile that I've highlighted in blue, if and only if it does not satisfy Q. In other words, Q is false in the structure for this given variable assignment. So again, similar to the previous slide, we now assume our primary connective maybe was conjunction as opposed to negation, in which case we're assuming that P is the conjunction of two well-formed formulas, Q and R. And again, because they are omitting this conjunction, Q and R have fewer connectives in them, and we can assume that both Q and R, we know whether or not the structure M satisfies those particular well-formed formulas with that variable assignment G. Now, we'll say that G satisfies P, that conjunction, in M, if and only if it satisfies both Q and R, both of the conjuncts. And in that case, we'll write that expression down there in blue with our double turnstile, which is exactly how we would expect the conjunction to work out in terms of satisfaction or in terms of truth. Now, for the case of disjunction, in other words, if this P was the disjunction of Q and R, then we say G satisfies P and M if and only if it satisfies Q or R, or possibly both of them, right? So we still say the disjunction is true even if both Q and R are both true. And again, we use that same highlighted blue double turnstile notation. Now, if the primary connective was the conditional, in other words, P was Q implies R, then we would say that G satisfies P and M if and only if it does not satisfy Q, or it satisfies R, or possibly both. In other words, just exactly what the truth table for the material conditional would say. And then again, we write this nice notation here with the double turnstile, including both the fact that we're working in the structure M and that we're using the variable assignment G. So our last truth functional connective is biconditional, and in this case, we say that P is satisfied in M with the variable assignment G if and only if both Q and R are satisfied or both Q and R are not satisfied. So let's now suppose that P is a universally quantified statement. In other words, P is of the form for all V Q. Here, Q may not have necessarily fewer truth functional connectives. However, it does have fewer logical symbols, and in this case, it has one less quantifier symbol, namely that quantifier symbol for all. And so we can assume that we've determined if Q is satisfied or not in this structure M. Now, we'll say that G satisfies the universally quantified statement P in our structure M if and only if for every D in our domain, Q is satisfied by the variable assignment G, where we replace that variable V with D. In other words, we go into Q and we replace V with every possible element from the domain of discourse, and we see if the resulting sentence is satisfied or not. And if it's satisfied in every case, we say that the universally quantified statement is true. It's exactly the meaning of the universal quantifier. And again, in this case, we write that nice double turnstile. You should take a moment to try and anticipate what the format for the existential quantifier will look like, because it's basically a very similar definition. So I hope that you were able to come up with the modification on your own, but the only difference between the universal and the existential quantifier is that instead of for every D in the domain of discourse, we have for some D. So if we can find some variable assignment that takes that variable V and plugs in D, resulting in something that satisfies Q, then we'll say that existentially quantified statement is satisfied by our structure M with that variable assignment G. In other words, what's highlighted there in blue. Now, because that's the last logical symbol that we could use to construct our well-formed formulas, that completes the definition of satisfaction for a given well-formed formula in our first-order language for this mathematical structure M and this variable assignment G. Before we go on to the soundness and completeness theorem, let's give just a quick example to try and solidify things in a concrete first-order structure. So here we're going to consider a new language that only has a single binary predicate. That's the predicate likes. And here I've labeled it with two variables, x and y. So there really are no constants in this language, just this single predicate and some variables. Now, the structure is defined via these three outputs because there's only sort of three logical symbols that we need to care about for this structure. That's the universal quantifier, the predicate, which in this case are likes and the identity. And then the constants, in this case, we don't have to worry about the constants because there's no constants to assign in this language. So the universal quantifier gives us out this domain of discourse consisting of Dan, Jane, John, and Marlene. So there are four people in this domain of discourse. And the predicate just lists out all of the pairs that make the likes predicate true. So in this case, the pair Dan and Marlene, John and Marlene, Jane and Marlene, and Marlene and Marlene. And the idea meaning that Dan, John, Jane, and Marlene all like Marlene. On the other hand, when we interpret equality or the identity in any structure, it always has to be exactly the same thing. And so in this case, it's the pairs Dan, Dan, John, John, Jane, Jane, and Marlene, Marlene. And those three together give us a first-order structure for this first-order language consisting of a single binary predicate. Now, let's further assume that G0 is the variable assignment with the empty domain, so it doesn't assign any of the variables, any of the elements of the domain of discourse. Now, the first expression we'll look at is on this first line, and it says that this structure M satisfies the predicate likes XX when we have the variable assignment G0, where X has been added to the domain of G0 and the output of X is Marlene. And the reason this is true is that when we look back at the interpretation of the likes predicate, this M of likes, that ordered pair Marlene is there. And so if we were to have replaced X with Marlene, we would get back something that is in this domain. Now, the second sentence there, the well-formed formula says there exists somebody who likes themselves. And notice there are no free variables in that particular sentence. And so it is appropriate for our variable assignment G0. And in this case, again, because Marlene likes herself, this particular sentence or this expression is true. In other words, M satisfies this sentence. There exists an X that likes themselves. The third sentence, that well-formed formula says there exists a person Y who is liked by everybody. And again, that person is Marlene here because Dan, John, Jane, and Marlene all like Marlene. Those are exactly the ordered pairs that satisfy this particular predicate and this structure. And so, therefore, for this empty variable assignment, this expression is satisfied in the first order structure M. Again, notice that it's appropriate for G0 because there are no free variables. On the other hand, if we swap the order of the quantifiers so that we have for all y there exists an x, such that likes xy, that sentence is saying that everyone is liked by somebody, and that's clearly not the case because Dan, John, and Jane are not liked by anybody, not even themselves. In particular, that means that the negation of that sentence is satisfied by our structure M for this variable assignment G0. So we're now in a position to make precise a definition that we introduced in the first couple of chapters, the notion of a first order consequence. So previously we had this vague idea of possible circumstances. And here we're going to solidify that by basically saying that a possible circumstance is one of these first order structures. So we'll say that a sentence Q is a first order consequence of some set of sentences, script T here, which we'll list out as P1, P2, and so on and so forth. If and only if every structure that makes all of the sentences in T true also makes the sentence Q true. And we'll write this nice double turnstile where we'll put those premises there on the left-hand side, script T, and the conclusion Q there on the right-hand side. This also allows us to introduce the notion of a first-order truth, or what we also call a first-order validity. A sentence P is a first-order truth if and only if every structure makes that sentence true. And in that case, we don't have any premises at all, so we don't write anything on the left side of the double turnstile, and we just say that P is a logical first-order truth. We'd also like to introduce a notion of the single turnstile for the syntactic notion of a proof. And in this case, if we have a set of sentences, script T, we'll write script T, then the single turnstile and P, to mean that there is a proof of the sentence P from the premises or some premises in script T using the full Fitch proof system, which includes the identity, introduction, and elimination rules, and the quantifier, introduction, and elimination rules. So here we don't include that subscript of a t because we're now allowing for, again, the quantifier rules and also the identity rules as well. So we're now in a position to state the soundness and completeness theorem for first order logic. Here we'll let script t be a set of sentences, either finite or infinite, and p be some sentence, all in our first order language. Now, the soundness and completeness theorem are the two sides of the following if and only if statement. There is a proof of p from the sentences in script t if and only if p is a first order consequence of those sentences in t. Now, the only if part is the soundness theorem, and the if part is the completeness theorem. The proof of the soundness theorem is essentially a straightforward adaptation of the proof for propositional logic. The difference is being that instead of a truth table, you're now looking at mathematical structures. And instead of just the rules for our truth functional connectives, we also have the rules for our quantifiers and for identity. Now, what that means in terms of the inductive proof is that instead of trying to preserve tautological consequence from our assumptions and premises, we would instead preserve first order consequence from our assumptions and premises. And naturally, when you're making an argument like that, you would assume that there's a structure that satisfies the assumptions and premises. But again, the proof is essentially a straightforward sort of adaptation of that. And when you look at the arguments for the quantifiers and for the identity rules, they're really just a reflection of the fact that those arguments are valid arguments in first order logic. So we won't go through the details, but the textbook, again, if you're interested, has a nice section that goes through the steps of that inductive proof. The remainder of the video will focus on the completeness theorem and the proof of the completeness theorem, which again is the if part of this statement. And what it says is that if P is true in any structure that makes the sentences in script T true, then there's an actual proof of P from some premises in script T that uses just our introduction and elimination rules for our Fitch system. Let's start by outlining the proof that we'll give here. But before we say something about the details of the proof, let me just point out that the soundness and completeness theorem that we're proving here depends on the Fitch style system that we've adopted. And that's not a feature of every first order logic. In fact, there are many different deductive systems that have been adopted for first order logic. The discussion for this week will ask you to look for some details of such a system online and post an example of something that you might have found. But I want to point out again that the proof that we'll give here is basically related to our Fitch style system. Now, what that means is that our proof has some components that are sort of built based on this deductive system that we've adopted, and then it has some components that are common to all completeness proofs. And I'll try to sort of delineate those two and focus on the sort of common component of those completeness proofs. Okay, so the outline of the proof that we're going to give here is a proof that was essentially due to Henkin in his PhD dissertation. But there are essentially 4 steps. First, we will expand our language via what's called the Henkin language by adding a whole bunch of constants. So we're going to add constants over and over and over and over again, and in fact, one for every well-formed formula. Once we get through that process of expanding our language, we'll be able to write down a set of first-order sentences that we'll refer to as the Henkin witnessing axioms, or the Henkin theory. And what this theory does for us is it bridges the gap between first order consequence and tautological consequence. And in step 3, that is made precise. Although here in this video, we won't go through the details of step 3. I'll leave that for the interested viewer to read on their own. And I'll point out what section of the textbook it comes in on. But the idea with the elimination theorem is that if you have a formal first order proof whose premises are either all sentences of the language or sentences from these Henkin witnessing axioms, with the conclusion that is also a sentence of your language, L, and so in this case, L is the language that we're working with, then you can eliminate all of these premises from the witnessing axioms from the proof in favor of a proof that uses the quantifier rules. So this elimination theorem will allow us to sort of first get a proof in the tautological sort of case, and then remove these assumptions about the Henkin theory to get a proof that just uses the quantifier rules. Okay, and then the final piece, and the piece that we'll focus on that's common basically to all the proofs of the completeness theorem, and really the most important part of this entire construction, is the Henkin model or the Henkin construction. And what happens is that for any truth assignment, and we'll say a little bit more about what exactly a truth assignment is, of the well-formed formulas that assigns this Henkin theory all true, right? So it marks all of those as true. Then there is actually a first order structure based on that assignment that makes sure that the sentences S that are satisfied by this particular structure are exactly the ones that are marked as true by this truth assignment. And on the next slide, I'll talk a bit about how we put all 4 of these steps together to prove the theorem. And then afterward, we'll focus mainly on step number 4. How do we actually construct this mathematical structure? So let's put the 4 steps together and walk through the details of the proof. We're going to begin by assuming that T is a set of sentences and S is just some sentence in our original language L, and that S is a first order consequence of those sentences T. Now, what it means for S to be a first order consequence of those sentences is that there's no first order structure which makes T union the negation of S true. Because if there was, then we would have a counterexample to that first order consequence. Okay, and then we'll use the Henkin construction to realize that there can be no truth assignment H which assigns true to all the sentences of T and the Henkin theory and the negation of S. Because if there were, then by our construction, there would be a first order structure that made the sentences in T and the negation of S true. And by our assumption, that can't be the case. Okay, so our Henkin construction is telling us there can't be this truth assignment. Now, if there can't be this truth assignment, what that means is that S itself is a tautological consequence of the sentences in T and the Henkin theory. And so again, this is that gap between the first order sort of consequences and tautological consequences that is bridged by this Henkin theory that we'll talk about on the next couple of slides. Now, the completeness theorem back for propositional logic then tells us that there must be a formal proof of S from the assumptions in T, but also from the assumptions in H, these Henkin witnessing axioms. Okay, so that's nice. We have this proof. However, it has all these extra assumptions from script H. Now we finally apply that elimination theorem to tell us that we can eliminate those premises from H in favor of just applying quantifier rules that we've established for our deductive system. And that means that we can then transform our formal proof into a proof of S from the premises in T that just uses our regular old sort of Fitch system, including the quantifier rules and the equality rules. And therefore, we can write script T, that turnstile, and then S as we sort of desired. Okay, and again, sort of the feature here that is common to all of these completeness proofs is this Henkin construction, the construction of this particular model. The rest of this with the quantifier rules is sort of a bit related to the setup for the Fitch-style deductive system that we're looking at. So I'll say a few words about the lemmas needed to get the last two sort of sentences to work, and then we'll focus on this Henkin construction. How do we build up this mathematical structure based on a truth assignment? Okay, so let's now go through some of the details of the various steps, and we'll finish with the Henkin construction. Recall that the first thing we have to do is actually expand our base language to include a lot more constant symbols. Now, the way that this works is that for each well-formed formula P in the language L with one free variable, we add a brand new constant symbol to the language C with a subscript of that well-formed formula. So we use the well-formed formulas to index the actual constants. Now, we let this new language that we obtained by extending by this new collection of constant symbols be denoted by L1. And that includes all of the language L plus these extra constant symbols, one for each well-formed formula P with one free variable. Now, when we do that, we introduce a whole bunch of brand new well-formed formulas that we couldn't have produced in L, but we can now produce in L1, because we can now use these new constant symbols in our construction to build up well-formed formulas with one free variable. Now, when we do that, we have to repeat the entire process again. So for each of the well-formed formulas P in the language L1, this extended language with one free variable, we add another new constant symbol to the language, C sub P, where again P is this well-formed formula in the new language. And we denote this extended language where we add these new constant symbols to L1 by L2. And again, we really do get a new collection of constant symbols or more constant symbols because there were new formulas in the language L1 that weren't in the original language L. But again, we run into this problem at L2, and so we can build up L3 and then L4 and L5 and so on and so forth. And we get this infinite chain of languages all sort of nested inside of each other. And if we denote our original language by L0, this sequence of sets is a sequence of subset relations. So L0 is contained in L1, which is contained in L2, which is contained in L3, and so on and so forth. And by our union axiom and the replacement axiom from axiomatic set theory, we're able to actually form the union of all of these languages. And we call the union, after doing this infinitely many times, the language L sub H. So we've now expanded our language by adding infinitely many new constant symbols, and we've done that infinitely many times, one for each of the new languages that we've produced. Now, this will be important for basically two different reasons. First off, it'll allow us to actually state what the witnessing axioms are. We need this expanded language. And then two, we will also use these constant symbols to build an actual structure when we look at the Henkin construction. So as we built these constant symbols, we sort of have in mind that they're eventually going to be sort of the elements of a structure that is going to witness the Henkin construction sort of lemma that we talked about before. Okay, so that's that process of adding constant symbols. And again, the reason why I'm sort of focusing on that more than some of the other steps here is that it's sort of a necessary piece in order to build up the Henkin construction later on. So now that we have expanded our language, we're able to state the Henkin witnessing axioms, or what the book calls the Henkin theory, denoted by this script H. Here it looks like a nice list, H1 through H5, but just realize that there are actually infinitely many different sort of statements that we're adding here. And in particular, one for every constant C and D in our language, and any formula P of X with one free variable. And these are coming from this expanded language where we added on all of these extra sort of constant symbols that were indexed by our well-formed formulas. Now, we needed to do that so that we could actually express the statement in H1, this expression about existential quantifiers. You'll notice that the rest of them don't really require this sort of extended constants, but nonetheless, any of the C or Ds that you're seeing, for example, in H2, H4, or H5, could be occupied by one of these new constant symbols. So we really do have a lot of sort of axioms here. Now, the second thing to realize is that each one of these axioms sort of encapsulates the details of one of our first order rules that we've been sort of using in our Fitch-style system. For example, H4 and H5 are basically the equality introduction and equality elimination rules, particularly restricted to the constants of our new language. H1 and H2 are the introduction and elimination rules for the existential quantifier. And then H3 is a way to sort of bridge the gap between the existential and universal quantifiers. And if we had put everything in Preenix form and followed the notion of skolmization, which was in the previous chapter, in chapter 18, we could get away with fewer of these sort of axioms that you're seeing here. But nonetheless, these axioms allow us to sort of bridge the gap between first order consequence and tautological consequence, meaning that these axioms here, all of our first order consequences will be tautological consequences of these particular axioms. So I went pretty quickly through the Henkin axioms in section 19.3, and I encourage those of you that are interested in the details to read the section. I'll do the same thing here for section 19.4. And partly the reason because of this is that these are details of the proof that are a bit more related to the deductive system that we've decided to adopt in our first order logic. Now, as I said before, there are many different deductive systems that you could adopt, and in some of those systems, the Henkin axioms are taken as just sort of axioms of the deductive system itself. So, sort of depending on the proof that you look at, this might either be part of the deductive system or sort of part of the proof. And this one here from section 19.4, I'll just sort of talk a little bit about some of the details, and then I'll leave the interested viewer to read the details of the proof in the book, which, by the way, goes by an induction proof, as does most of the theorems in this particular section. Okay, so it's the elimination theorem, and it's proposition 4. It's one of the steps that I outlined at the beginning of this sort of proof of the completeness theorem. And it says that if you have a formal first order proof of a conclusion S from a set of sentences in your language L, whose premises are sentences P1 through Pn of L, plus some sentences from this Henkin theory, right? So this extra sort of statements. Then there has to exist a formal proof which they denote by P prime. So you can sort of rewrite this into a formal proof, P prime of S, with just the premises P1 through Pn alone. And in that process, you replace those extra premises that came from the Henkin theory with sort of instances of the introduction and elimination rules for quantifiers or for equality. And again, the proof here goes sort of by induction on the length of the proof here. But again, it's sort of dependent on the system that we've adopted. So if you're interested, I would say this is a great section to read up on the details. So we're ready now to talk about the Henkin construction and finish off the proof of the completeness theorem. Now, in order to do that, we first have to start by saying a bit about what a truth assignment is for our expanded language L sub h. So you can think of a truth assignment as being the row of a truth table or a joint truth table. However, now we have to actually specify the truth values of all the atomic sentences as opposed to just the atomic sentences that are appearing in the premises and conclusion of the argument that we're analyzing. So a truth assignment starts by specifying those truth values, and you're free to choose whatever you would like on the atomic sentences. Just like in a row of the truth table, you're free to sort of pick out the true and false nature of the sentences as you would like. Once you assign the values to the atomic sentences, you can then use basically the definitions of the well-formed formulas and the meaning of the quantifiers and connectives to assign truth values to all of the sentences in the first order language. Okay, so once you have truth assignments for the atomic sentences, you can sort of expand it out. And here we'll be looking only at truth assignments that mark the sentences in the Henkin theory that we talked about earlier, that's that H1 through H5, as being true. So those are the only truth assignments that we'll look at. Now, if we have a truth assignment like that, it can have true and false marked for any other atomic sentences that it would like, and then whether or not the sentences, the more complicated well-formed formulas are true or false, can then be extracted from that sort of base information about the atomic well-formed formulas. And when that's the case, there is a first order structure, M, which will depend on H, so we're going to include that subscript of H, such that for all the sentences S that were assigned true by this truth assignment H at the very start of all of this, so basically in that row of the truth table, the structure satisfies that particular sentence. So in other words, it makes that sentence true within that particular structure. Okay, and that's why it's called the Henkin construction, because you're constructing this first order structure that makes that sentence S true. Or those sentences S true, which were marked as true by the truth assignment. Okay, so how does the proof work out? Well, first off, we're going to fix an arbitrary truth assignment that assigns true to all the sentences in our Henkin theory, script H. So that's just sort of handed to us. And on the other sentences, the atomic sentences, it can have whatever values it would like. Again, remember then, the more complex sentences, we use sort of the truth tables and the definition of the quantifiers to then build up the truth values of those. And we let D prime be the set of all constants of our expanded language. Again, there are many of them because we went through this process of repeatedly adding more and more. And what we'll be able to do is introduce a brand new binary relation, which turns out to be an equivalence relation on this collection of constants. And the way that you do it is the following. You say that C and D are related by this binary relation. where C and D are elements of this domain of discourse consisting of the constants, such that the truth assignment marks C is equal to D is true. So the truth assignment thinks that the constants C and D are the same. The relation we introduced on the previous slide on the constants of our expanded language, which we're now denoting by D prime, turns out to be an equivalence relation. And by an equivalence relation, we mean a relation that is reflexive, symmetric, and transitive. And when that happens, the domain here, that D prime, gets split up into a collection of equivalence classes. And we'll talk a little bit about those equivalence classes. Those will actually be the elements of our Henkin construction on our next slide. But for now, we'll focus on why it's the case that this relation that we've defined on the constant symbols is an equivalence relation. In other words, reflexive, symmetric, and transitive. So let's go through this step by step. First, reflexive means that for every constant C in D prime, C is equivalent to C. And the reason this is the case is that in our Henkin theory, for all of the constants in our expanded language, C equals C was one of our axioms. And one of the assumptions that we made about our truth assignment at the very start of this sort of proof of the Henkin construction was that our truth assignment assigned each of the statements in the Henkin theory as being true. So by our definition of this this relation that we're proving is an equivalence relation, we know that C is equivalent to C, or C is related to C. Now, we'll say a bit about why it's symmetric. So let's suppose that we have two constants, C and D, in our expanded language, so elements of D prime. We want to show that if C is related to D, then D is related to C. So we can sort of flip this around. And this follows from the fact that in the Henkin theory, we adopted the sentence of P of C and C equals D implies P of D. And this was related to basically equality elimination in terms of our Fitch-style system. But because we assume this is true for any well-formed formula with a single free variable, we can assume that it's true for the sentence P of X, where P of X is taken to be X is equal to C. And when that's the case, it says X is equal to C and C is equal to D implies that C is equal to D. D is equal to C. And just in terms of tautological consequence, what we find is that if the truth assignment had marked this particular sentence as true and C and D were in fact related to one another, then the conclusion here would be that D would have to be related to C. Okay, so again, another one of our axioms from the Henkin theory. Now, the last is that this relation turns out to be transitive. So in this case, if we assume C, D, and E are all constants in D prime, and that E is related to C and C is related to D, we'd like to show that then E has to be related to D, sort of bypassing the C. And again, this comes from the same axiom as before, but now we take, instead of the sentence X is equal to C, the sentence E is equal to X. And what we get then is if E is equal to C and C is equal to D, then E is equal to D. And again, because that sentence had to be marked as true, and if the two sort of hypotheses of that conditional statement here for transitivity, that E is related to C and C is related to D, are also true, well, then we can conclude that E had to be related to D. So again, another sort of conclusion from the fact that we were marking everything in the Henkin theory on this truth assignment with a value of true. Now, again, what happens when you have an equivalence relation is that it splits up the domain, in this case d prime, into a collection of equivalence classes. And the equivalence classes are those things that are sort of related to one another. Everything being related to itself means that it sort of splits it up into nice sort of chunks. And we'll denote one of these sort of chunks, or the collection of things that are equivalent to some constant c, by just putting some brackets around that particular constant. So those will be all the other constants that are equivalent to c. And these turn out to be the actual elements of our structure. So on the next slide, we'll start to define the details of our structure M sub h. So now that we have our equivalence relation and our equivalence classes, we can define the details of the actual Henkin structure itself. We'll denote the domain of discourse here has D, and D turns out to be the set of equivalence classes of this equivalence relation for that set of constants, which we were denoting by D prime. Now, typically in a lot of mathematics classes where you use this notion of equivalence relation, you call this the quotient, and you're sort of quotienting out by this equivalence relation. And that's the notation there on the right-hand side of this D prime with the slash and then the relation. But from here on out, we'll just call this collection D, and it's just the collection of all possible equivalence classes where C is one of these constants in this expanded sort of Henkin language. Now, remember, for a structure, we have to interpret the predicates, the functions, and the constant symbols. And once we do that, that basically identifies our structure, and it tells us basically how which sentences are, satisfied by this particular structure. Okay, so if P is an n-ary predicate, then we let the sort of domain here, or the interpretation of that predicate, be the collection of n tuples of equivalence classes of constants C1 through Cn, such that the truth assignment marks P of C1 through Cn, and this is the well-formed formula P here, with those constants C1 through Cn actually plugged into the values of this predicate, is marked as true by the truth assignment that we started with at the very beginning of the proof. So basically we're saying, so we're just going to collect together those equivalence classes that were marked as true from the truth assignment. Now, this same thing can be done for the function symbols, but in this case, we need n plus 1 ary sort of tuples. So we need that extra n plus 1th value to denote the actual output of the function. Now, the textbook has a really nice sort of example of this in the very last part of the proof, and there's sort of a canonical choice for this C of n plus 1. But here, we don't really need a canonical choice. We just need one that sort of works, and there's always an example of one that does. And here, we'll sort of collect together those tuples that are marked as true by the truth assignment. And again, remember, that is sort of an atomic sentence there, because we've got that equality predicate and then two terms on the left and the right. F here, being a function symbol, still only gives us a term. Okay, so that's how we'll interpret our function symbols. And then finally, we'll interpret all of our constant symbols to simply be the equivalence class of that particular constant. So if we have two constants that are equivalent, say C and D, then they'll get mapped to the same sort of object in this particular Henkin structure. We're basically done with the proof here, but we need two sort of key results. One is to ensure that the previous construction that we used was actually sort of well-formed. And the second is to get the conclusion that we wanted from this particular construction. Neither one of these I'll go through the details of, but I'll just leave the interested viewer to read through the sort of inductive proofs in the textbook if they're interested. Now, the first sort of key result here is that if you have a sequence of constants, let's say C1, C2 through Cn, and you have some equivalent constants, C1 prime, C2 prime, Cn prime. In other words, they're in the same equivalence class. Now, if that's the case, then the truth assignment will mark P of C1 through Cn true if and only if it marks H of P of C1 prime through Cn prime true. And what this means is that even though we used a particular constant in our definition on the previous slide for our equivalence class, we used sort of a representative for our equivalence class, this ensures that it doesn't matter which one we would use. So we're free to sort of pick any one of them. Now, if this statement wasn't true, then we would have sort of run into some issues with our previous definition, and it would have depended on which of the representatives of our equivalence class we chose. Now, the second is that by the way that we constructed this, we can now use induction on the number of connectives in S to prove that for any sentence in our expanded language L sub H, that this structure satisfies that sentence S if and only if our truth assignment that we started out with from the very beginning, which made the Henkin theory true, also marks S as true as well. And notice that at the atomic level, that's exactly sort of the way that we constructed our structure. So we made sure that at the atomic level, this particular sort of sentence was true. And then the inductive proof just goes by connective, showing that the statement remains true for any sentence S. Now, the induction is a bit subtle here, and it is on the complexity of the term as opposed to the number of connectives here. So you should be a bit sort of careful, but those that are interested can check out the details. And that sort of concludes everything that you'll need for the proof of our completeness theorem, and that's the end of this particular video. In our next and final module, we'll say a bit more about the incompleteness theorem, which is also a result of Kurt-Gödel that was deduced a year later. And it says a bit about what happens when we have some axioms that sort of assume the piano arithmetic, or these statements for a piano arithmetic, or in some sense can be, as we've seen with ZFC, you can interpret the statements of piano arithmetic with sets. We'll find out that if you have some axioms of those form, then you can run into some problems and run into sentences that are true but don't have a proof. But we'll say more about that in the next video.